In this video, I'm going to be discussing the adiabatic approximation. So the adiabatic approximation for a changing potential for a quantum system. And so what is an adiabatic process? And so this is one where the external conditions change much slower than the internal conditions. And so when this happens, the internal conditions are unaffected, or at least unaffected enough that we can just call it unaffected. So kind of an everyday example. So think of carrying a cup of coffee. You want to move slow so that you don't disturb the liquid and cause a spill. So you want the internal conditions of the coffee, so the sort of just the random movement of the water molecules in your liquid will remain at a state of equilibrium. But if you move quick, the movement of the molecules in the cup would be disturbed and you would cause a spill. So you want to sort of move it adiabatically. And so another example, and this is the one that is used in the Griffiths textbook, is a pendulum in a box swinging back and forth. So you can picture it like this. So you pick up the box and move it. If you do this slow, the movement of the pendulum will not be disturbed. But if you move it fast, the pendulum swinging will become chaotic. And so we have the external conditions occurring in time t sub e. So this would be moving the box with the pendulum inside. And the internal conditions occurring in time t sub I. So e for external, I for internal. And here the t sub I would be the swinging of the pendulum. And so the adiabatic means this, that the time it takes to do the external thing is much greater than the time of the internal thing. So the pendulum is swinging back and forth in this box here, and that's happening much quicker than the person is carrying it. And so now we can consider what's called a non-holonomic pendulum. And so non-holonomic is just a fancy word for meaning that the state of it will be different after the adiabatic process than it would be before the adiabatic process. So we have our pendulum here that's swinging, and say we have it swinging sort of in this direction as we start at the North Pole and walk down this path to the equator, at which point we do a 90-degree turn and start walking that way until we get to here. We do another 90-degree turn and walk back to the North Pole. And so the pendulum will be swinging in this direction as we walk down here. It'll be swinging in the north-south direction as we walk there, and here it will be swinging in this direction. So the direction at which the pendulum is swinging will be changed by this uppercase theta here. And I guess I should also point out that we're assuming a non-rotating Earth, which is another one of those fun assumptions you can make when doing physics. But the reason that we want to assume that is because, as we will see, the Earth rotating actually does this for us, and so we can use what's called a Foucault pendulum to actually measure the rotation of the Earth using this process here. So yeah, here I'm just explaining what I did. So you start at the North Pole, you go to the equator, and you walk some distance, making an angle uppercase theta. And the change in the angle of the pendulum swinging will be this theta. And we can find the area enclosed by the path. So that would just be the area sort of inside here. So first, the surface area of a sphere is 4 pi r squared, but we're only looking at the northern hemisphere here, so we can multiply that by 1/2. And then we multiply it by the fraction of the entire 2 pi radian angle that this theta makes. And so that's sort of the fraction, the ratio of the number of radians we went to the total number of radians for a full rotation. And so we get this. So this is the area of that space. And then when we cancel things out, so this will cancel with that and that. the pi will cancel with that pi, and so we just get this theta r squared. But if we take this to the unit sphere where our radius in all directions is 1, then we get this. But in general, the omega here is going to be equal to the area divided by this r squared, and so that is actually our solid angle that I discussed in a previous video. And so if we want to look at the Foucault pendulum, so we have this right here to get the solid angle that we move. So we're doing a line integral here, and we're doing it here in polar coordinates. And so we want to look at the d theta and d phi. And so a Foucault pendulum, so say you are, we have z here at the North Pole, and you are some degrees here from the North Pole, and that degrees we're calling this theta sub naught right here. And so this time we're actually saying that the Earth spins, and so we are looking at what happens after you make a full rotation. So if you start here with your Foucault pendulum, one full day, one full 24 hours passes, and you end up right back here again. So yeah, the Earth is rotating. We have a pendulum set up on a line of latitude. We can then integrate the angle subtended by the path. So that is this, remember. And so this will be our phi here, which will just end up being 2 pi, and then we have the integral for our theta angle here, and so we end up with this 2 pi times this negative cosine of theta sub naught, and we're going to do that at 0 and theta sub naught, which gives us this right here. So at the equator, we would have the theta equal pi over 2, and cosine of pi over 2 is 0, and so that would be 2 pi right there. So our omega would be 2 pi. At the North Pole, we have cosine of 0 equals 1, and so we'd have 2 pi times 1 minus 1, which would just be equal to 0. But if we look at an intermediate place here, so if we look at Grand Rapids, Michigan, which is where I live, this is at a latitude of 42.9634 degrees, which is roughly 0.75 radians. And so if we look at this omega, we have 2 pi times the 1 minus this cosine of 0.75 here. So we have this 2 times this 0.268, which gives us roughly 0.54 times pi, and so it's roughly pi over 2 radians. And so what that means is that the Foucault pendulum would change angle by about 90 degrees, or 2 pi radians, after a full 24-hour rotation of the Earth. And so that is a way that you can actually measure sort of the rotation of the Earth, is using one of these Foucault pendulums. So the strategy is to solve for the external parameters held constant, and then at the end allow them to vary slowly with time. So for a pendulum of length L, we have this as our period here, and if we allow the length to change slowly, then we would have this, where now our L is a function of time. But now if we start talking about this in quantum systems, so we are changing our potential, and so our Hamiltonian will change. So we consider the adiabatic approximation when we transition from this Hamiltonian at time 0 to this Hamiltonian at time uppercase t. And so what the adiabatic theorem is this, what I have in bold. So it is that if the particle is in the nth eigenstate of this of the Hamiltonian at time t0, then after slowly going to this Hamiltonian at time t equals uppercase T, the particle will be in the nth eigenstate of this Hamiltonian. And so we're looking at these two different Hamiltonians here at different times after undergoing some adiabatic process. at the time t equals 0, this is in the nth eigenstate of this Hamiltonian. Then after we undergo the adiabatic process, it is now in the nth eigenstate of this Hamiltonian right here. So the energy and will change, but the fact that we're in the nth eigenstate will not change. And so, for example, we have an infinite square well where this is our wave function that we got in a video quite a long time ago. So if we move one of the walls from A to 2A, so doubling the width of the potential well, then we end up with this. So we have to put a 2A in for each of these A's. That one will cancel with that one, so we end up with this. So like I said, the energy is not conserved, so the energy is lost from the system as we make this expansion, but the process is started in the nth eigenstate of this Hamiltonian, and the new eigenstate is the nth eigenstate of this Hamiltonian for any t during the slow change. And so this is what we're doing, where we have this a here, then we double it in size to 2a here, and this will be the same eigenstate of the Hamiltonian with this potential as this will be the as this wave function here for the Hamiltonian in this potential right here. However, if the well is expanded suddenly, then for a moment after you expand it, so we see that the wavelength here of our wave function is the same there as there. So it'll still be in the nth eigenstate, but now that nth eigenstate is a linear combination of other eigenstates of the Hamiltonian there. And so before this kind of expands out to take up the area here, it will still be in that nth eigenstate, but the nth eigenstate is a sort of complicated linear combination of eigenstates for the Hamiltonian at some time. All right, so in an adiabatic process, although the eigenstate remains the same, there is, however, a phase change. In fact, there are two ways the phase changes. And so there is this one that I have here in green, which is called the dynamic phase, whereas e to the I times this right here, which is just this integral right here. So we see that that is a function of the energy in time. But there's also the geometric phase, which is this e to the I gamma sub n of t, which is this integral right here. And this integral right here is very interesting. So it's similar to the Aharonov-Bohm effect. In fact, it's sort of a generalized Aharonov-Bohm effect. So the Aharonov-Bohm effect, which I talked about in a previous video, is a sort of particular case of this geometric phase shift right here. So I'm not going to go into too much detail on this stuff, especially this. If you are interested, so if you want to sort of see a derivation of this right here, this video, which will be linked to in the lecture notes, which I have linked to in the description down below, is great. And he goes through sort of the entire derivation for that. Then he also has a video called Berry's phase, which is sort of about this integral right here in particular. And so if you want to look at that, then check out this video right here. Though this video, if you don't have any background in electrodynamics, then you might get a little lost in that one. And so I actually have here some recommendations for books on electrodynamics. So Griffiths has one that is often touted as being very good. So Griffiths is the same guy who wrote this quantum mechanics textbook that I've been using. So he has this textbook. I also highly recommend this one right here. So this guy here, this Jacob Schwichtenberg, sorry if I butchered that name. I've only ever seen it written. But he has sort of a whole series of no nonsense. He also has a classical mechanics, a quantum mechanics, and a quantum field theory, no nonsense. But this electrodynamics one is pretty good too. It doesn't go into as many things as this one will, but it'll give you, all of the things that you essentially need to know to, understand most things that you'll encounter in electrodynamics, at least, at this sort of introductory level. So I also would recommend this one right here. So this is of these Students' Guide to series, and this is about Maxwell's equations. So it's even less detailed than even this one right here. But it's very short. It's a very short read. It's to the point, and it uses a lot of diagrams. And these students' guidebooks are all pretty good, but I especially like the ones that this Daniel Fleisch authors. So they all have a lot of them have different authors, but Daniel Fleisch has authored several of them, and the ones that he authors are really good. And this book in particular is really good if you want to get like a good intuitive understanding of the Maxwell equations. But anyway, that was everything I wanted to talk about in this video, and in fact, that was everything that I wanted to talk about, or even that I can talk about, from the Griffiths textbook, The Introduction to Quantum Mechanics. So I'm actually finished with that book, as I mentioned at the end of the last video. So I will be making more quantum mechanics videos, and in particular I want to do a series on interpretations of quantum mechanics. So, like the Copenhagen interpretation and the pilot wave theory and all those kinds of things. So I think those are where I'm going to go next in this quantum mechanics playlist. But anyway, I don't want to ramble on too long. I hope you found this video helpful, and I will see you in the next one.